We are discussing line scanners. This may seem like it's a little out of place because we've been discussing digital image processing. It's a question of where the digital image processing comes within the course. I have to discuss all that so that you can do the labs that are associated with it. So we talked about fixed frame sampling. Then we talked about digital image processing. And now we're back to talking about the other major kind of sensor, your line scanners. Right. So there are three kinds of sensors. The frame capture sensor, where you're collecting the entire image all at the same time. The cross-track scanner or the whisk-broom scanner, where the field of view, okay, what's being observed at any one time is moving back and forth, left and right relative to the direction of the sensor and picking up brightness values as it goes. And then the long track scanner or push broom scanner, where you have an array of detectors that cover the entire swath. So one detector for each pixel across the swath, and you're pushing those forward. Now, film and digital frame capture systems are limited to the visible and near infrared range of the spectrum. There are no satellite versions of mid-infrared and thermal infrared fixed frame imagers. To collect data beyond that range, line scanning systems are required. So we're going to talk about the basic design principles of these sensors that create images, but by building up images one pixel or one line at a time. And here I just give you a little table to help you remember the differences. Frame capture systems, a grid of detectors is used. Cross-track scanner, a single detector. A long track scanners, a line of detectors. Frame capture systems, you can use them for the visible and near IR. Cross-track scanners, you can use for the visible, near IR, mid IR, and thermal in IR, which is the same for the long track scanners. Frame capture systems build images by collecting grids of information simultaneously. Cross-track scanners build images by moving optics to focus a single pixel on the detector. And then long track scanners build images by passing a line or a narrow array of detectors over the scene. As always with me, if I put in a table like this, I'm probably going to ask you questions about it on the next test. So this just gives you a better idea of what's going on within a cross-track scanner. There's a rotating mirror. Okay, the rotating mirror is changing that field of view. That's what we call it on the ground. The field of view where the actual observation is being made. That then goes into a series of focusing optics. It then goes into a dichroic grating, and you can think of that as operating the same way that a prism does. It splits out different wavelengths of light. It's used though to split out wide ranges, so visible, near IR, MIR. You can see that some of that light is being bounced up to a mirror and being fed into a prism, And then that light is being guided toward, we have 5 different detectors in total. And each of those detectors translates the amount of light being observed into an electrical signal. And the brighter the radiance, the more powerful the voltage that goes into the electronics. And then that goes into a storage device to be held, on a satellite system, to be held until there's a good window for downloading the data. Cross-track scanners, I should say, are the older technology. They only rely on a single detector, and the technology for miniaturizing these detectors into a long track scanner just didn't exist. It just didn't exist, excuse me. So this gives you an idea of what a cross-track scanner is actually seeing. It's seeing a varying input voltage that varies with the brightness that's being observed at any one point. And there's a sampling process that goes on. So there's a process in time, there's a sampling interval over which an average brightness is being recorded. Now, a cross-track scanner has a lot of physical parts to it, and it's got that rotating scan mirror, but it also has a compensation mechanism. If you look at the little figure there to the right, as the scanner is moving back and forth, the spacecraft is actually traveling forward. Okay, so you don't get with uncompensated analysis or sampling, you don't get a nice image. What you get is a series of overlapping lines, and you have to have a correction for that. So there's actually another set of mirrors that move the field in view back while one scan is being made, and then when the other scan is being made, so that you wind up with an image with pixels in parallel lines. Having moving parts in space kind of sucks because there's no way to get up there and repair them, even if it's a very simple problem. And we have a very simple problem with the scan line corrector on Landsat 7. So you can see the image there. There are lines in between the actual data, those black lines. And that's because the scan line corrector seized up and stopped working. And so as a consequence, you just got these parallel lines. And there's been a lot done to try to come up with clever ways to fill in the data that's missing, but ultimately there's no way around this problem. Your data just is not complete. Fortunately, this was Landsat 7. Landsat 5 continued to work throughout the period that Landsat 7, between the time Landsat 7 failed and Landsat 8 was launched, so we continued to have data. One thing you should know is, although we display pixels as a square element, it actually has a circular footprint on the ground. Because if you think about it, optically, if you take a flashlight right, and you aim it at something, you don't get a square. What you get is a circle. And so all of optics works the same way. There's really no way to sort of cut off the edges. So the definition of an imaging system actually is a system in which the observations are either adjacent or overlapping. And in these cases, in remote sensing, generally with scanning systems, they are slightly overlapping. And the term we use is the instantaneous field of view, is the actual area on the surface that's observed by any one pixel. We use field of view to mean the swath of data that's being collected by a sensor, and we use this instantaneous field of view to give you the actual area of the surface that's being collected. Now, cross-track scanners have displacement. Now, on the left, we're looking at a fixed frame image, and if you remember, the displacement on a fixed frame image is from the center, right? Because you're looking down only at the principal point. Are you actually over a particular area? The further away you get in both dimensions, the more displacement you get. Well, that's the kind of displacement being shown in the photo and in that first image, sort of the middle image there. But that's not how one of these line scanners work. The displacement occurs from the center line of the image. So if you think about it, you're no longer getting anywhere along that red line. You're directly above the surface. So that becomes the area of zero displacement, and you have displacement in the other dimension, and the displacement gets larger the further away you are from that center line. Spaceborne platforms are very stable. Airborne platforms are subject to movement due to air currents. Now, frame capture sensors capture every pixel simultaneously, so every pixel is properly located with respect to all the other pixels. So you get some problems with it. You know, you can get roll, pitch, and yaw, and that can lead to further processing errors, but it's always going to look like an image. Cross-track scanners capture each pixel of an image sequentially, and so as a consequence, they're subject to the highest level of distortion because the plane can be moving in any direction relative to its location where it collected the last pixel. Long track scanners capture each line on an image separately, so at least each pixel in a line is properly located with respect to all the other pixels in the line, but subsequent captures can be distorted. And that image on the bottom just gives you an idea of the different kinds of distortion you can get with a fixed frame versus the various scanning approaches. So we talked about cross-track scanning. A long track or push broom scanners are a definite improvement over a cross-track sensors in that they don't require the mechanical and optical components needed to sweep the detector back and forth. And particularly in space, anytime you replace a mechanical device with a solid state device, you see an improvement in reliability. So, you not only have the mechanism that's sweeping back and forth, you also have that scan line corrector that led to problems with Landsat 7. Displacement is the same as with a cross-track scanner, but all the pixels across track are properly aligned to each other. And the ability to have a large number of pixels, greater than 10,000 in any given scan line, and to have multiple scan lines in an array allows for greater flexibility in sensor design. So we're going to talk about one kind of line scanner that has capabilities that you can't get with a fixed frame sensor. We're talking about hyperspectral scanners. I'm just going to go over this table again. At the top, we're looking at a little diagram of what the spectral range is. We have the optical and the visible. We have the near infrared, and then we have the mid infrared. That next line down shows in red, the relative exoatmospheric spectral irradiance. That is, if you were just outside of the atmosphere and you took measurements of the brightness as a function of wavelength, that's what you get. Along with that, I've got atmospheric transmittance. So in values that are high means that there's a good percentage of light getting through the atmosphere. I then put in 4 different spectral signatures. And then at the bottom, I've got 4 different sensors. So QuickBird has 4 bands, red, green, blue, and near infrared. TM adds in the 2 mid infrared bands. MODIS brings in a, 7th band that is used for atmospheric correction. And then at the bottom, we have a hyperspectral system. In particular, this one is AVIRIS. And AVIRIS has 224 bands. So rather than trying to select areas in the spectrum that are going to be useful, AVIRIS actually records everything. It requires, it used to have a 10 nanometer width. The current generation of AVIRIS has a 5 nanometer width and twice as many pixels. And it's just collecting all that data, even though some of that data we know for land surface purposes isn't going to be very useful because it's going to be in areas outside of atmospheric windows. This will give you another idea of the AVIRIS concept. For AVIRIS, every pixel is a continuous spectrum. So if you're looking at vegetation or water or soil or the atmosphere, you always are getting a full spectral return. Okay, so each pixel can be thought of as multiple co-registered or individual series of reflectance values in the different wavelengths. And you can see at that image on right, you have a much greater amount of information in hyperspectral images, and that can allow for more definitive identification of surface types. So this allows 2 capabilities. The first capability is spectral matching. So you can have laboratory samples of, for instance, various ores or clay types or vegetation, and you can go through pixel by pixel and say how similar is a particular pixel to one of those references, and at least tentatively identify the surface as the spectrum of the sample that it best matches up with. The other concept that we get with hyperspectral data is spectral mixing and unmixing. So spectral mixing is a physical process. All sensors are integrated, reflecting light from multiple elements within a pixel. So within a pixel, you might have grass and a tree and a termite mound, some savanna area. But the light from that entire area is being integrated into a single set of numbers. And so when a pixel is not uniform, and normally it's not at some degree, spectral mixing occurs. So what's spectral unmixing? Well, if a mixed pixel is the sum of the pure spectra weighted by the area of each material, well then if we know what the pure spectra are, then the fractions of each cover type can be mixed. So over there on the right, we've got 1 pixel, and we've got it broken up into 3 cover types, A, B, and C, and it shows the percentage of each one that covers that pixel. And then we have 3, what we call an end member. Those are the unique spectrums that are in the pixel. So we have A, we have B, and we have C. And then by taking A and multiplying that by 0.25, B multiplying that by 0.25, and C multiplying that by that 0.5, we then see the mixed spectrum, just the weighted average of the first 3 unique spectrum. The math gets complicated quickly, but if we look in this image at the upper left, what we're seeing is and it's hard to see on this flat image, a 3D scatter plot of points, and one end member, unique spectra, is labeled in green, that's vegetation. There's another one that's labeled in blue, that's soil, and the red one is, the one labeled in blue is water, and the red one is labeled, those are all soil pixels. So every other point can be expressed as a mix of those 3 end members, just based on their distance from the particular point to the center point of each one of those clouds of end members. So what that allows you to do is, well, first we're just looking at a color infrared image. We then have a vegetation fraction image. So for each point, we can determine what fraction is represented by one of the end member spectra. Okay, we have a soil fraction, a water or shade fraction, and then finally we can get an error image. That is, we can say, well, if we're correct about vegetation, soil, and the water shade fractions, then we should be able to mathematically calculate what a pixel just made up of those 3 components would look like. And then that's not going to perfectly explain the pixel observation, and therefore we have this RMS error, root mean square error image, that explains how well we did explaining the overall spectral variability using those 3 fractions. You can see there are some places we did well, some places we did poorly. It looks like there must be multiple kinds of soil in here, because Some of the soil areas we seem to be doing very well, and some of the areas we seem to be doing a poor job. So it's an interesting observation. There are a variety of hyperspectral sensors. As you might expect, they're quite complicated systems. And so as a consequence, there are not as many of them. AVIRIS was the first hyperspectral system made by NASA. CASSI is a system developed by a private company. The Eagle is also a private company sensor. HIMAP, private. Hyperion was a spaceborne system developed by NASA that is hyperspectral, but it's lower spatial resolution. I believe it's 30 meters. There it is, 30 meters in resolution. And then CRIS is an ESA spaceborne system, and that's 20 meters spatial resolution. They've got between 126 and 288 bands. The key thing about these systems is they don't always have the spectral range you'd like to see. So AVIRIS is sort of the standard. It has between 400 nanometers and 2450 nanometers. So that's a good section of the mid-infrared. CASSI only goes out to 1050, or at least it didn't until the most recent model where it achieved 2450 nanometers. I believe that requires two different sensors. The Eagle, again, limited at about 1,000 nanometers. HIMAP does go out to 2500, and as does Hyperion. The CRIS probe, I don't know why they call it that. It's proba, actually. And that's between 400 and 1050 nanometers. So it's useful, but the mid-infrared is pretty important. So not having the mid-infrared is a big problem. The spatial resolutions for the 4 airborne systems are variable, as you'd expect with altitude, and Hyperion and CRIS are again 30 meters and 20 meters. So what can you use hyperspectral for? One thing people have used it for is agriculture, and one of the applications they've got are water applications, and also disease applications. So small differences in the color of leaves can indicate the onset of disease. It's also been used for invasive species mapping. Site remediation, because it tends to be very good with geology, finding ores, for instance, that might have some kind of contamination problem. It's been good at water resources, algal blooms, detecting an algal bloom that is poisonous from one that isn't. That's an application that's been developed. And finally, general geology, being able to detect directly ores or surfaces that are associated with ores has been a big application. And finally, it's been used just for plain old land cover mapping, and you can get sort of a higher classification resolution. That is, rather than just saying this is a wetland, you might have, as in this classification, high marsh, Phragmites, which is common reed, stunted Phragmites, so areas where it's not growing well, high marsh Phragmites, Spartina, which is a reed that grows in more saline water, and then mud and water. But those are possibly classes you wouldn't be able to pull out from something like Landsat. And then vegetation identification and invasive species. This is a 3D image of a Hawaiian rainforest depicting the encroachment of two invasive tree species that are represented as either pink or red upon the native trees that are displayed in greens and blues. And then the low vegetation in the foreground is an agricultural field. So they're doing, this actually has two sensors. It's got a LiDAR sensor that gets you the three-dimensional aspect, and then the hyperspectral, which allows you to tell the difference between native and non-native species. When we talked about displacement, one of the things we learned is that the higher the altitude of the sensor, the less displacement you would see. The higher you go, the greater the extent to which basically every point looks like it's at nadir. Which is great if what you want to do is create stereo models from airborne systems, but from space, you might want to create airborne from space, you might want to create digital elevation models. And because of the displacement, you can't do it from a single platform. So you need to take images from two different positions, which requires off-nadir pointing. So either forwards and backwards along the track of the satellite movement, or to the side from which we call a cross-track stereo. A cross-track stereo is effective, but it can be delayed by the need to wait for an appropriate orbit and the possibility of cloudiness in either the first or the second path. Pointing forward and then back at the same area, it's going to be much more likely that it's going to be cloud free at both times. And you don't have to wait for a second orbit in order to make the observation. Some satellites can make observations in that fore and aft orientation and produce stereo imagery during that single paths. Others actually have two sensors that are fixed and point in the fore and the aft orientation. So they're actually set up to do forward and backward observations at the same time. And those systems will also have a nadir pointing imager. And this is actually a very it's a concept that is being pursued quite heavily by NASA because it gives you 3D images, right, all at one time. And it could be very, very useful for monitoring things like changes in geology, so shifts in tectonic plates, but it could also be useful for observing the canopy surface elevation. The concept here would be that you would collect a data source like LiDAR that allows you to see the bottom, allows you to see the terrain elevation, which is very difficult because it's an active sensor technology and you can only sample a very small area at one time. You add on, though, this other much simpler system, and you can then get continuous updates of the elevation of the canopy surface and therefore you always have an estimate of canopy height. And there are sophisticated airborne systems that use this concept of a nadir, a fore and an aft pointing sensor. There's a system out of the German Aerospace Center. The one that I'm more familiar with is the Leica ADS-40. So each has three 12,000 pixel push broom sensors and a single nadir looking multispectral sensor. And so they're capable of generating imagery of 25 centimeters at about 12,000 meters above ground level. So 38,000 feet, essentially, the altitude of commercial airline airplanes. And then the accuracy of the stereo coverage is 15 centimeters in the horizontal and 20 centimeters in the vertical. So this is very precise stuff. And you're getting a multispectral image that's perfectly orthorectified because you have a perfect DEM that you've gotten from your fore and your aft pointing sensors.